first, how does it work, the exercise class? So you have a sort of list of exercises for today, and then you will receive. It's already finished and it's ready. We are going to send you the new sheet of exercises next week, and as you can see, there are several exercises that you can try to solve. And in this exercise sheet, there is no, let's say, hardcore exercise. But in the next one, there is an hardcore one, and then there is an XXX, really hardcore. I mean, it's really difficult, and we are going to discuss, somehow, I would like to, we should be more relaxed during this lecture. We should discuss about exercises. I'm going to give you some comment and solution of some of the exercises that you have in your exercise sheet, and then what? And then there are other exercises that you can do by yourself. In particular, for PhD students, how does it work? Because, I mean, somehow exercises are used to give a sort of evaluation, but clearly we are all friends and we can try to agree some smart way to do it. So I will give you maybe 5 or 6 exercise sheets during the course. And clearly I'm not expecting that you do and write down all the exercises, because it would be crazy and maybe you are not interested so much in this stuff. And so I would like to solve 2 exercises for each exercise sheet, and without any preference. I mean, you can choose the exercise to solve, the easier one or the harder. I mean, it's not important. And someone asked me for the deadline. So far, who cares? I mean, no deadlines for the exercises, but since my contract will end at the end of May, maybe, let's say around the 10th or 15th of May, we can meet and we can discuss together exercises in order to have a sort of evaluation about the course. And now another announcement. We are social, so we have a YouTube channel with lectures, and I don't know how to find it because I'm a boomer. And okay, so YouTube channel and math departments. I said YouTube and on other stuff. And there, I mean, in this channel I will he's going to collect actually, all the lecture that we are going to have, and in order to have somehow, if someone is not here, he can follow, if he wants, the lecture on YouTube. Quite social. More thing to say. So next week, it's important. Next week, no lecture on Tuesday, but the lecture will be moved to Thursday, the 20th, maybe, I don't know. Where, I don't remember. Somewhere. And you will receive an email containing all the information about the room, and also for the room, let's see the email that you will get. And in the email you will also receive the next exercise sheet for 2 weeks. Not 1, but 2 weeks. And other information, I don't know. Let's see. Maybe not. So we will try to somehow stabilize the room, and clearly starting from the end of the February we reserved Seminario 2, but I will try to discuss politely with some other people and ask maybe a change in the room because it will be difficult since the lecture starts and it's not easy. And we can start. So today we can, let's say, discuss a little bit the exercises that you have in the exercise sheet. So far what we have seen, let me recall you. So far what we have seen is the definition and the properties of topological groups and then last time we introduced the notion of R measure for locally compact Hausdorff group. And then we talk a little bit about the modular function. And so the exercise sheet number 1 will be a sort of collection of exercises regarding these notions, and in particular, if I remember well, because I do not have the sheet with myself, the first one is like to show the fact the orthogonal group of PQ is compact if and only if either P or Q is equal to 0. The second one should be given a suitable neighborhood of the identity. There is a smaller neighborhood such that its square is inside the neighborhood V, and then what you have, I don't remember. And the other two are related with R measure and something like that. So today I would like to start like discussing a little bit, actually solving the first one, and then we are going to move to the one with modular function, and then we are going to discuss the modular function for GLN R, and then maybe if we have time also something else. We will see. So the exercise 1, the exercise is show that OPQ is compact if either P equals 0 or Q equals 0. So somehow the content of this exercise tells you that there are only specific cases when this group is compact, which is exactly given by this condition, and this gives you exactly the group. So notation P plus Q equal N. So in particular, if either P equals 0 or Q equals 0, then what you get is the group ON, which is exactly the classic orthogonal group that you maybe saw in linear algebra or whatever. So, solution. So let's start. Let's discuss a little bit how to proceed in solving in such an exercise. So, idea. So do you know that ON is compact? Yes or no? Yes. So how to show it? Let's recall the fact. So ON. So let's recall the definition of OPQ. We have JPQ defined by what? The identity of order P, 0, 0, minus the identity of order Q, and OPQ by definition is given by what? The element in G and R such that transpose JPQG JPQ. Right? So there are matrices preserving the bilinear form with signature P and Q. And so in particular, when either P or Q equals 0, you get that ON is the set of matrices such that this is exactly the identity, right? So how to show that this group is compact? Since you saw, maybe you can recall me because I don't remember.
It's closed because it's a country image of 0 of a continuous map.
Sure. So let's write it. It's closed. Why it's closed? Because we can consider the following map. Take an R. Actually, you can restrict it to GLN, but it's not important. Take any G and consider the following map. Then, by what we show, I don't remember, maybe the first lecture, this map is continuous, and its restriction, it was crucial that its restriction to G and R was continuous, because in that case you get that it's a topological group. So in particular, this continuous map, you can consider the preimage of the identity here. So ON, let's call P, is P minus 1 of the identity. So in particular, ON is closed both in MN that in G and R. Okay? And then what?
It's bounded.
Why it's bounded?
If we use any norm, for example, the minus 1, which is not very Euclidean, every matrix in ON has a norm.
Maybe it's easier to use the operator norm.
It's mean of the n, for example, because it's
Okay.
I don't know how to say.
I mean, if you somehow the let's say the right norm to look at is given already by this condition, because you know that the orthogonal group preserve the Euclidean, the standard Euclidean bilinear form, and in particular, if you use the operator norm, these are isometries, and hence they have all norm equal to 1. So it's easy to see that. Another way is to see the following fact is the fact that if you take the trace the identity, and then this is equal to the trace of TGG, but this is equal to the sum of the square of the elements. So it's in a sphere, in a suitable sphere of the Euclidean space. And please check this step. So On is closed and bounded in somewhere in Rn square, and hence it's compact. Done. Okay? So On done. So let's say that one direction it's easy. So the other one. So how to show that if P or Q are, both P and Q are not equal to 0, OPQ is not compact. Any idea? So when you have a problem, what's that? To understand what's happening, what's maybe the starting point to start play the game? How it's easier to? Sure. Let's start using dimension 2. So maybe we're here. So it's easier to fix the dimension equal to 2, and then to understand what's happening in there. So assume now two things. The first, that both P and Q are strictly positive, and now we are going to fix ourselves in the case n equal 2. This means that P equal Q equal 1, right? So we need to start with a group of 1, 1, which is whatever. And so one of the possible ideas is to take G equal to A, B, C, and D, and try to impose the condition that this metric preserves the bilinear form of signature 1, 1, and try to see what happens. And you get, because I need to copy, you get what? Let's see. C square minus A square equal 1. AB equal CD, and B square minus D square equal 1. These are the equations that you get. Let me say that these are equivalent to G, J11, G, J11. Okay? Hence what? So any nice formula that you already saw somewhere. So what you do for parametrizing the orthogonal group, if you have the orthogonal group, if I remember well, here you have plus, right? And you use the fact that the cosine square plus the sine square is equal to 1. Here you have a minus. So, hyperbolic, yes. So, in particular, here the idea is the same, but you need to use the hyperbolic sign and the hyperbolic cosine in order to express the term that you have. So, in particular, recall that we have the following identity. Okay, adesso sbaglierò. probabilmente, cos square minus sine square t equal 1. Giusto? Giusto. Ok? Ci piace? So, and hence what? So in particular, I recall that one, I think the sine has this graph, I think, and the cosine has this graph. So in particular, we can find a value of t such that we can write a in terms of the hyperbolic sign and then use it in order to express c. Okay? So, in the end, what we have is that let's take what? Define X, the set of matrices given by, sto già invertendo? No, è giusto. Hyperbolic sign t cos ht cos t sin ht with t in R. So what? So this is for what we have said so far. This X is inside O11. Okay? And if you want to check, you can also take this matrix and verify by yourself that the matrix times J11 blah 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 is equal to J11. Okay? But now you can see directly that this group is not compact. This object is not compact. Because as t goes to infinity is not bounded, for instance. So this object here is unbounded. Right? And then you have an unbounded object in O11, so in particular O11 cannot be compact. So at least for n equal 2 we are happy. And for higher dimension, why? I mean here there is a trick. You have your X which is unbounded, so for sure O11 is unbounded. And the next step is to find in OPQ O11, because if you find another stuff which is isomorphic as a group inside O11, isomorphic to O11 inside OPQ, you are done. So strategy the strategy now, so let n now be strictly bigger than 2, and the strategy to find a copy, an isomorphic, let's say correctly, an isomorphic copy of O11 or even of X, it's not important, inside OPQ. Okay? And so somehow I need to find I need to find an injective map, let's say I from O11 into OPQ, right? So far so good. Any idea?
Blocks, a matrix like that, not with blocks.
So the idea is exactly to realize somehow O11 is a diagonal block inside here. So one of the possible inclusion, there are many, but one of the possible inclusion of, let's say, A, B, C, D can be the following. So we divide by A prima. So these are what? P, and these are, no, questa essere PP, quindi qui, Q, Q, okay. So here nothing, nothing. So here we put, except that here that we put A, B, C, D, 0, 0 and blah, 0 and 0 and blah, and the identity. Is it clear how we construct this matrix?
-1.
No, because you want to, I mean, this matrix preserves, and if you multiply T this is exactly this one, but here you have -1 and not here, because it's not important, I mean. Okay? So you realize that a copy, an isomorphic copy of O11 inside OPQ, but you know that O11 is not compact because it's unbounded. So in particular OPQ cannot. So it cannot. Hence OPQ is not compact. Compact when both P and Q are strictly positive. Okay? Question about the exercise. Is it clear? Everybody? Okay. So somehow you saw that the strategy is to find something smaller and smaller and smaller in the group which cannot be compact, and then arguing by step by step, that the bigger group is not compact. That's the main strategy in order to solve the exercise. And so starting from the next week, I'm going to start, I mean, maybe we are going to start really enjoying the stuff that we are going to see, because I will start the argument called homogeneous spaces, and there is like tons of mathematics behind and the column somehow, and we are going to discuss tons of spaces that you have already met, like projective spaces, like spheres like whatever, but realizing them in a different way. And in particular, so the compactness of ON is somehow important and related to its natural action on the n-1 dimensional sphere, because if the sphere can be realized, we are going to see it as a suitable homogeneous space starting from the rotation group. And this will have tons of consequences, like for characteristic classes, like for homotopy groups, whatever. And its cousin, which is OPQ, and both P and Q are strictly positive, it's instead related to, let's say, in the specific case when either P or Q is equal to 1, it's related with the hyperbolic space, which is somehow the right word where you can think about stuff which is negatively curved, or whatever is the content of this strange statement. So somehow now words in freedom, and so somehow when so we have ON and we have OP, let's say n-1. And here we are going to study its action on the n-1 dimensional sphere, and somehow this is the building block for spherical geometry. And for n-1, 1, here you have the hyperbolic real space, and this is the starting point for hyperbolic geometry. And then you can move on, maybe. And I think, if I remember well, I don't know if it's true, but maybe you can correct me, O22 is somehow related to a space called anti-de Sitter of dimension n, and it's somehow related to something which is not strictly Riemannian, let's say. So this is a Riemannian word. Somehow we are going to see that there is a well-defined notion of Riemannian metric. Maybe you already saw in the course of curve superficie, surfaces and curves. The first fundamental form of a surface is the natural Riemannian metric for the embedded surface in R3, and coming from the Euclidean one. And so we are going to generalize this notion, and I will spend like 4 hours, maybe more, I don't know, talking about Riemannian geometry, and we're going to see how this stuff is related to our world. So besides this craziness, we can move on. Any question not related with this stuff? If not, we can what we can do, let's see. Cosa voglio fare nella vita? Che famo? Salute. Prego. What we can check? Maybe this one, which is quite easy, and then we can have a break and then start again in the next hour. So this is this strange fact that we are going to see that maybe it's exercise 2. So let G be a topological group, and so let V be let's say an open neighborhood of the neutral elements, e lo vogliamo connesso, so connected, open connected. Then what we can check that there exists another neighborhood of the identity of the neutral element, e.g. such that first is symmetric in the following sense, and then such that, let's write this way, its product with itself lies inside V. And so this is quite strange. I mean, somehow the idea is that you have G, you have your neutral element, you have V, and somehow you can find, let's say, a more symmetric neighborhood W inside V, such that its product with itself is still inside V. That means that somehow this should be W squared, it's still inside V. And one can ask why I should care about this property. Well, because it's important for several reasons. For example, in the first exercise in the first point of exercise 3, the existence of this neighborhood is crucial in order to prove the so-called property of left and right continuity with respect to the group structure. And we're going to see this. But also in the next exercise sheet, the first exercise is convolution of a continuous function with compact support, and somehow this exercise allows you to prove that convolution of functions which are continuous and compact support is still continuous with compact support. So how to show this strange property? Any idea? So you have what? You have, so V is an open connected neighborhood of the neutral element, and the only thing that you know is that G is a topological group. What does it mean to be a topological group? Or what's So in particular, since G is a topological group, we know that both the multiplication and the inversion are continuous. So we have to use either the multiplication or the inverse map. Which one? I mean, we have to move a little bit more. So we need to use something. So how many of you would you like to use the multiplication map? Raise your hand. Nobody? I don't think so. Maybe someone wants to use the multiplication map. So, sorry? I mean, you ask for both property.
I think I should take the backwards image of U by the multiplication and then try to restrict it for even further.
Yes, somehow that's the idea. Somehow you have that the multiplication map is continuous, so for sure the preimage with respect to the multiplication map of your V, it's open, because it's continuous. So since it means continuous, what you have is that the preimage of E is open. Right? Guess what? Who cares? No, it's important. It's open in the product topology. And the particular base of the product topology is given by rectangles, squares, whatever. I mean, given by thing of the following form. So in particular, this is open, and moreover, it contains neutral element, common neutral element, right? Because the identity multiplied by the identity is the identity. So for sure, this element is there. But now, this object is open in the product topology. So what? So there exists V1, V2, open neighborhood of the neutral element such that V1 times V2 lies inside here. Again, who cares? But now what? Now you want to build a neighborhood of the identity, and let me say that both V1 and V2 are neighborhood of the neutral elements. So what we can take, the intersection. So take U, define U in this way. We are done? No. Because we also want the other property which is symmetric with respect to the inverse. So what we can do, define W. No. U intersecting U minus 1. And now you are done, essentially. So define W as U intersecting U minus 1. So the idea, carino, vero? The idea is to exploit the property of continuity of the multiplication in order to somehow restrict yourself every time to a smaller neighborhood that satisfies the property that you want. And indeed, you start by considering the pre-image with respect to the multiplication, and take these two objects and blah, blah, blah. But now, I feel that maybe I should ask any question about this exercise. What has maybe Rita Fioresi, are you happy with this or not? Let me tell you if it's true or not. Are you agree with me? I mean, are you W is correct, is not correct? Comments, something like that.
I understand why mu minus 1d.
Suspense?
Includes, Oh, no, sorry.
What?
No.
So W lies both in V1 and in V2.
Sorry.
So you're saying why, you don't understand why maybe
No, I didn't understand the first thing about
this one.
Yeah.
So mu is continuous. So in particular the pre-image of open set, it's open. And in particular what you have is that it contains EG times EG, because you are fibering somehow that you are considering the pre-image with respect to multiplication, and in there, in V, you have the identity, and there you are taking back the pair neutral element times neutral element.
How can I be sure that W is not void except identity?
I mean, it would be, you're taking an intersection of open sets, so it must be open. And it will be identity, what means that the identity is both closed and open, and so it's a problem. I mean, we are not taking the trivial group. Okay, G is not a trivial group. Let me think. So maybe you can take so maybe it's not, but you can take the connected component of containing the identity. Because you know that, you can take that. So yes. You can restrict yourself to the connected component of the identity. You have no more questions, we can stop for a break and then start again for the next hour. Yes. Thank you.